Hello and welcome back to my YouTube channel. In this video we're going to see how we should solve these two integrals that I defined up there of 0 to infinity of sine x squared dx and cosine squared dx. So I'm just going to remind you that these integrals graph look something like this, which is an even function, and I can indeed write them as half. For example, I can write integral from 0 to infinity of sine of x squared dx as half of integral from negative infinity to infinity of sine x squared dx. So I can do that, and it's a property of the even functions. Now what I'm going to do, I'm going to recall you of the Euler's formula. E to the ix is cosine x plus I sine x. Recall that here. So what I'm gonna do, I'm gonna define an integral from negative infinity to infinity of e to the negative x squared dx, which is the Gaussian integral, and that's why we're using it. You're gonna see why. And I'm gonna substitute root a x in the power, and you later see why, because I want to do a clean, smart substitution. I want to say root ax equals t, thus dt equals dx root a. Thus my dx is dt over root a. And if I do this substitution in my integral, Gaussian integral, it's e to the negative t squared dt over root a. This is the constant in our integration, thus it can be factored out and moved out, sort of. So it's the integral of negative infinity to infinity of e to the negative tx squared dt, which this integral is the Gaussian integral, and the integral from negative infinity to infinity of e to the t negative tx squared dt has the value of root pi exactly. Thus I can write this as root pi over root a. Now what I can do, I can substitute I for the a here. I'm allowed to do this. So now my integral is going to become root pi over root I. And can I proceed any further? Yeah. Root I is a 0 real part plus 1 imaginary unit, which is square root of negative 1, which has a property of I squared equals negative 1. Recall the imaginary and complex plane, where the imaginary is defined as the y-axis and real as the x-axis. Now my function, my imaginary number here is defined as this under the graph as 1 imaginary unit, and the imaginary numbers can be written as r e to the I theta. My length is 1 because I just got 1 imaginary unit, and my angle is 90 degrees here, which is I theta, I pi over 2, and it's going to become I pi over 4. So now I can write e to the I pi over 4 as cosine of pi over 4 plus I sine of pi over 4. Therefore, it's going to be root 2 over 2 plus I root 2 over 2, where I factor out root 2 over 2. It's going to be 1 plus I, an imaginary unit. If I then, if I then multiply both sides by the square root of 2 to rationalize it, actually I'm gonna first, so this is root I, I'm gonna plug it in here, so it's gonna be root, it's gonna be 2 over root 2 root pi, 2 over root 2 root pi divided by 1 plus I, And if I multiply both sides by the root 2, it's going to be 2 root 2 over 2 root pi or 1 plus I. The 2's are going to cancel out. It's going to be left with root pi root 2 over 1 plus I. Oops, let me correct it here. 1 plus I. Now, if I multiply both sides by the complex conjugate of the denominator, it's going to be 1 minus I, and thus I obtain the result, that is 1 squared minus I squared, where the denominator 1 minus I squared, which is 1 minus negative 1, which is 2. Thus, it's going to be root 2 root pi 1 minus I. If I multiply both sides by square root of 2 again, I'm going to get this result. It's going to be 2 root pi 1 minus I over 2 root 2, which is going to be root pi over root 2 1 minus I. Thus, my integral that I was looking for here is, my integral is root pi over 2 minus root pi over 2I. Okay, now we can proceed further here by recalling the whole integral here to be integral from negative infinity to infinity of e to the negative x squared dx. Now, I can expand it again using the Euler's formula. It's going to be cosine of negative x squared plus I sine of negative x squared dx. We know that cosine is an even function, thus the negative is going to be absorbed to it. It's going to be cosine of x squared dx. And the negative here is going to be coming out because sine is an odd function. And it's going to be minus I negative infinity to infinity of sine x squared dx. The whole thing equals to root pi over 2 minus root pi over 2 minus I root pi over 2. Do you see the pattern? Well, the integral from negative infinity to infinity of cosine of x squared dx matches this root pi over 2 exactly. And if I multiply it by half, I'm going to get, from this theorem that I stated here, property of even function, if I multiply it by half, I'm going to get its integral from 0 to infinity. Thus, if I say, oops, this is supposed to be root 2, root pi over root 2. Did I do it correct? Yes, it's correct. I just forgot to include root 2 here. Okay, now root pi over 2 root 2 is integral from 0 to infinity of cosine x squared dx, which can be written as root pi over root 8, which is root pi over 8, and thus our integral from 0 to infinity of cosine x squared dx is root pi over 8. I'm gonna indicate it here. And if I do the same thing for the other integral of mine, integral from 0 to infinity of sine x squared dx, it's going to be root pi over 8 again. So these two integrals both have an exact value of root pi over 8. But here's the thing. How are we even allowed to put I, imaginary number, in A here? Let me know in the comments what you think. So thank you for watching my video. If you enjoyed it, please like and subscribe, and I will see you next video.